So in this tutorial again, we're gonna enhance the exploitation that we wrote in previous tutorial, in particularly the tutorial 6.2, the advanced exploitation. So in those particular case, we use, we use the bin shell, a bin shell string as a way to get the shell by creating symbolic link. So because we are so lazy to inject proc flag, or we couldn't find the proc flag string in the memory space, then instead of crafting those string in the server side or in the program's memory space, we just utilize any string as part of this payload. And then because we have complete control over local environment, we create a symbol link from any string to the proc flag. So whenever the program attempt to read any string, then they're gonna read the proc flag as a result. But unfortunately, you don't have this luxurious controllability in remote setting. So in other words, if you don't have proc flag string, you're the one who have to inject them. And this is what we're gonna talk about today. So at high level, we like to demonstrate in two things. We're gonna, similar to one of the challenges that you saw in previous lab, we're gonna craft proc flag string by utilizing existing string in libc. As you can imagine, there are a lot of proc related string because proc is a common path or standard path for libc functions to utilize. Like for example, proc self, proc map, all these stuff should exist in libc space. But these are the characters that we're gonna take advantage of them. And also, as you can imagine, there are tons of flag string as well. It's not complete flag or proc flag, but given these two strings, we can easily concatenate them in a way that we can utilize those strings as a result. So once we know about these two space in libc, and we're gonna formulate those strings in this one of the buffer that we are using for file name, and as a result of memcpy, we're gonna have a proc flag string in temp2. Once we have that, we're gonna utilize this open read write exploitation to get. And then we're gonna talk about a more fancier way to get this by invoking this read function. Instead of utilizing existing data in the memory space, we're gonna utilize the read function. In other words, if you invoke read with the standard input, and as an attacker, you can start communicating with the server environment. So as a result, you can actually put whichever string you want inside this temp directory. And after that, you can take advantage of the same payload that we wrote in tutorial 6.2, right? Let's go to the previous advanced ROP. So this is what we wrote last time. So if you run the program, you get the flag by using symbolic link. If you delete this read, if you delete this shell, you shouldn't get the flag, shouldn't read the flag, because they couldn't access the flag through the shell file that we provided as a symbolic link. So let's restore this, and we're going to extend this program in a way that we can, even without this shell symbolic link, we're going to still inject or craft whichever string that you want to utilize in remote environment. So let me briefly overview what we did. We create a simple ROP chain. In the first ROP payload, we're going to leak GOT of the puts by using the PLT of the puts, so that they actually dump the address of the put function in libc. From this leakage, we calculate back the libc base from the offset that we got from the local environment. So starting from here, in fact, we can now ready to utilize any functions in libc. For example, we infer system libc functions by using this libc base and offset and bin shell string that we search in the memory of the libc module, and some of the gadget for third argument in x86 64 environment. And similarly, we have open, read, map, write as a result. So let's clean this one. And once we are done with this first payload, what's interesting here is that we're gonna return back to the main so that we can restart the program effectively. But at this point, we can still launch the ROP attack, but by using the existing leakage up to here, because in the first payload we leaked the address. We basically break the layout of the libc, so that at that point of the time, in fact, we can utilize all existing gadget plus all the function calls in libc like this. In this case, for the convenience, we wrap around, create these core 3 functions that basically set each argument by using the pop gadget that we found, and then ultimately invoke these functions. So if you specify core 3 open and bin shell, and this is bin shell is pointing to the bin shell string, but we really need a relative file name so that we calculate a little bit so that we can bypass the path separator in bin shell. And then after that, we read this file descriptor so that we can load the probe flag into the buffer and write to the console. And the way we pick this 3 number is based on how many file descriptor that this program is using. In fact, this program never open any other file descriptor or files in system, so we can easily guess. Or if you don't want, you can actually reliably create the way to fetch the RAX and put it to the first argument of the read as well. But it's completely unnecessary in this setting. And we also set the breakpoint in a way that right before executing the ROP, we have a chance to debug the systems in pretty convenient way. Okay, this is basically it in our payload, and our first task is to formulate the probe flag instead of relying on this bin shell. The one caveat, unfortunately, because the way we implement these core 3 functions is extremely inefficient. So whenever you restart the main, you almost spend most of the stack space. So we better break this payload into another payload so that we basically have a 3 type of payload in this program. So let's restructure a little bit, but still we hope that we can still maintain the features as we want. So after this, instead of crashing, then we like to jump to the main. What's the main function? Okay. See, we can continue. I think it's already almost out of. Let's break this one. So what if we delete this 2 guy? Right? You can see the password as a result. So we like to create another stage. Let's move this. Okay. Let's keep this open and read the result. So what we just did, in the second payload, we just open a file, and then by sending this guy, and then in next payload, we're gonna send the rest of the ROP chain, so that we have more space to put like memcpy and stuff in here, and we still have opportunity to utilize this open read system call. So let's try whether this one is actually working. Okay, it actually iterated 3 times, and then because you see all this password stuff 1, 2, 3 times, right? The main loop is executed 3 times, and the second and third payload are executed concurrently as well, in sequence as well. Once they open, they execute read and write pretty easily. So it's time to craft our payload. So this one is better for debugging. So our first plan is the memcpy to one of the buffer. In this case, we pick the buffer here. Because it's in the middle of nowhere, it's basically contain null. If you are not familiar with, and memcpy actually getting 3 parameter is destination that you're gonna copy to, and source, which you like to copy from, and how many bytes that you want to copy from source to destinations. But ideally, what we want is that we can copy proc, say, proc something into the buffer. So how many characters we have to copy? This amount, right? So that we can copy from the string up to here. And then we're gonna copy the rest of the string from some flag related stuff into flag. So by doing this, by executing this, buffer will contain proc flag as a result. And because the buffer already contains the null bytes, we will have correct C string as a result like this. That's great. Let's find out these memcpy functions in libc. Let's first to search those string. Because we already set the breakpoint here, it's easy to search the string as well. So what are the proc in the program? In fact, there are too many. Let's pick something in data section. But it really doesn't. You can pick any place you want, and calculate the offset in the libc. And let's find the flag. So we got this on 2 locations, and also we can invoke memcpy, or unlike Ubuntu, my distribution is all sorts of memcpy. The main reason behind this is that modern implementation of libc tend to utilize the hardware capability. So whenever you invoke memcpy, they're not just providing naive implementation of memcpy. For example, if your system has AVX extensions or SSE instructions, then try to provide those vector instructions so that they can accelerate the memcpy. So how they can find out the hardware capability typically is determine the compilation time. Because your hosts support this type of instructions, your compiler can take advantage of them. But unfortunately, as a distributor perspective, we cannot kind of guess what end user might have in their CPU. So what they came up with is the idea that whenever this type of function is invoked, they dynamically figured out what type of what version of the program they want to utilize, and that's what we call these I functions. And this is a POSIX standard extensions or something that they can leverage those type of I function behavior in kind of indirect call. But if you find this T function is actually in the text section, you can still find the naive implementation of memcpy. So in our case, we should pick this memcpy so that among all these interesting memcpy implementations, and we like to use this particular one. Let's see how this one is actually different between them. What's the base? This is the base, and I like to show you these two different implementations. This is a memcpy implementations. As you can see, it's very short. Whenever you provide this copy by using this very nice instructions and return back. Indeed, this one is actually copying this. Unlike this, other memcpy instruction, and this is a 2.14, and actually this guy, right? You can see from the bottom, both are same. So by default, and they're gonna provide those memory pointer that pointing to this optimized version of memcpy, so that loader can figure it out the best possibility or best performant implementation by utilizing your hardware capability. So here, the implementation is a little bit different. As you can see here, in fact, they have bunch of checking in a way that this particular case, this particular location is a fetch the hardware capability of the system and compare whether this one match, and this particular number represents certain hardware capability. Whenever it match, it fetch some of the, I'll say in this case, fetch necessary functions. In this case, move AVX on line, move AVX on a line, ERMS, and by default they return and move ERMS. Basically, just comparing the hardware capability and return the function pointer as a result. It's not an actual memcpy that you can imagine, right? But if you disassemble this one with perhaps using Jydra, and this is how does it look like. And this is a typical memcpy. There are many symbols behind this memcpy implementations, and this is the memcpy that we just saw. Or if you just specify memcpy or just use memcpy in your C program, this is the function will be invoked as a result. But in fact, linker, when first memcpy is invoked, linker kind of take advantage of this memcpy so that they will fetch the best implementation of memcpy and relocate this one for you. So the actual memcpy pointer that you're gonna contain in GOT table is a result of this execution. But if you just utilize this particular address, and you will just evaluate the possibility a best implementation of memcpy in your systems as a result. Again, this is not the actual memcpy that you like to invoke. The memcpy that you like to invoke is another implementation that actually performing memcpy. In fact, this assembly is much easier to read rather than this. So what they ultimately do is just copying all the memory based on the length restrictions. But in terms of this assembly, it's very hard to read, as you can see here. So we picked this memcpy for actually copying source to destinations instead of previous one. This one is much easier to read. Okay, this is actually copy operation separately, right? That's good. Let's utilize. We have everything we need. Let's pick this memcpy. Okay. Okay. So before we open, we like to invoke this two memcpy function. 3 memcpy. It's our first argument. We like to use the buffer. We define the buffer. Yeah. So it's okay to share the buffer that you're gonna load the flag and at the moment that you open the file, because these are two different moments of executions, right? Whenever you at the moment that you invoke the open functions, buffer is really for open system calls. Then we're gonna provide the proc. We like to copy up to the second path descriptors of the proc. And then we're gonna concatenate this guy. And how many flags do we like to copy? How many characters do we like to copy? C, proc, and flag. Okay, sounds good. Let's see this one's actually working as expected. Because we set the breakpoint here, so it's about to execute this memcpy, meaning that we're about to set the argument of the memcpy as a result, and return, and first gadget, and second gadget, and we are on the memcpy. Right? Check the argument. This pointing to the buffer RDI is the first argument. I guess this is all just zero value, because we are about to invoke. Second argument contains the proc string, the proc self map, and the third argument is a length. In this case, is 6. Let's invoke and finish. And we just finished the execution of the first memcpy. And then we are about to execute the second one. Before we do that, we can check. Okay, check the content of the buffer. We put the /proc/, which is the result of first execution, right? And let's create another one. And we are about to execute the memcpy. Right? Let's finish. And hopefully in here we have everything we need. Right? We have a proc flag. So because of these two invocations, we kind of have buffer in the proc flag, and then we have everything we need. So instead of using being shell, we provide the proc flag. Let's delete this shell, and then see if we can execute. Oops. I think the second one is not. Let's move this guy. See? Oops. As you can see here, once you're done, after you formulate this proc flag inside the buffer, by using this proc flag, which is a string located in buffer, we open the files and read and write to the console. So we get this the flag without actually utilizing the symbolic link in the local environment. That is about memcpy. But another fancier way to do this, instead of utilizing the existing strings inside the libc, but we can directly inject whichever string that you want. So for this, we're going to do much simpler way. In fact, we like to invoke like this: read, input, and buffer, and probably length of the probe flag. This ultimately we like to invoke. We can, we already have read functions, right? So we can do buffer as the first, 0 should be the first argument, second argument, and length probe flag. So by invoking this, the program, while running this, they're actually waiting for the user's input. So at the point that right after we send this, we have to wait until the program reaches the executions, or simply you can wait by sleeping or something. You can also wait, but you can wait until the password, right? Prompt and send more profile. So I think we better wait here to check whether probe flag is correctly inserted into the program. Let's see, it's working. So we set the breakpoint right before we send the second payload. We already send the probe flag as part of the string. So hopefully, while executing, this read call and read call accept the probe flag as a result. And see, let's check the buffer. Let the buffer. Yep. Yeah, it seems they already have the probe flag, right? So because we already set the probe flag in the program, you can get this. Password. See, if you want to read any files in system, this becomes universal shellcode or payload. That whichever you specify in here will be translated in terms of exploitation code, and you will actually get the file out of the systems. What's interesting here is that because we precisely specify how many characters we like to read, and we don't actually have to send anything more than the file name. For example, even new line character, for instance, because the program will only accept this amount of character that we like to put as a result. And there are a few things to be careful when writing those exploitations. For example, if you don't wait here, what's happening here is that, in fact, you cannot actually run, sometimes you can, but most of the time it doesn't work. It's not reliable. The reason behind this is that this send, again, program is extremely fast. If you send these two packets together, under the scene, they actually buffer in your operating system. In the end user, in this case, the counterparty, this particular program, will accept the entire string as a bulk, so that the payload will be accepted as if the string is appended here, which is right before your read is executed. The previous call that accepts this payload, maybe scanf or read, depending on the implementation of the target, will consume all the characters that we are sending and put it to the end of the buffer, which is exactly what we want to avoid. One unreliable way to avoid this is set the sleep. Maybe you can say 1 second and wait until that. Hopefully the counterpart consume all this payload and start executing, we later send this file, so we can avoid such a problem. But this is a very unreliable and slow way to get this, so we better to synchronize the moment at this point with the exact string that we can be used as a result of the execution of this guy. So I think that's all for today. You can easily extend this one to launch against the remote. Hopefully, you don't have much trouble converting that for remote versions. And it seems like a good trick that you should be familiar with to solve the later labs.